So let's look at the physics of roller coaster loops. Once again, Jimmy, much like much of what I've taught you this year, this is actually garbage. We don't build roller coaster loops in perfect circles anymore. The first one built, I'm going from memory, I'd have to look this up, I believe it was in Coney Island in 1933-ish, in the 1930s. And all it was you climbed a big high platform, you got on a cart, it went shushing down the hill, there was a loop at the bottom, and you got off. But it was hugely popular. But the problem is, if you're doing a circular loop, the G-forces on you, the normal forces on you, are tremendous. They had to have a permanent nurse's station, an ambulance station at the bottom of the ride. Most people would get off with nosebleeds, whiplash, some people would black out, but it was still hugely popular. It was great fun, excellent! Of course, now in our current society, you couldn't get away with a ride like that, because you'd get sued like crazy. So what we build roller coaster loops in, if you look at them from the side, they're actually sort of teardrop shaped. The fancy word is it's a clothoid loop. It's a loop of constantly decreasing radius. And by doing that, you can dramatically reduce the speed required and therefore the G-force, normal force that you're going to hit at the top and bottom of the loop. Having said that, that level of physics is beyond us right now. So here's our circular loop. Let's look at it. A roller coaster barely makes it around a vertical loop of radius 4 meters. A says, find the minimum height that the roller coaster needs to start from at the top of the hill. Okay. So we want to find that. It says minimum height, so I think we're going to assume that we're starting at rest. And the key word, the word I want you all to underline is this: barely. It barely makes it around the loop. And the trick to analyzing this is not to start at the top of the hill. The trick to analyzing this question is to start right there at the top of the loop. Trust me. First of all, in this question, is there a change in height? Yes. Is there a change in speed? Yes. Is it a curvy, yucky path? This is going to be a job for conservation of energy. And what we need to figure out is how fast you need to be traveling at the top of that loop if you just barely make it through. Because that'll tell me how much kinetic energy you have there. Then I can extrapolate, work my way backwards, and figure out how much energy I better start out with. So we're going to go to conservation of energy. But first, we're going to start at the top of the loop, and we're going to say to ourselves, self, what are the forces acting at the top? Get the obvious ones. What word did we underline? We'll even circle it right here. That tells me if I barely make it, because how heavy you feel is your normal force. If you barely made it, you would feel like you were going to fall out of the roller coaster. You would not feel like you had any mass. You would be clutching at your seatbelt. Thank God you had your seatbelt on. I think barely means no normal force. The normal force at the top is 0. Which really means this: winner equals circular force. And I knew to go to the mv squared over r, because I said we're going to be doing conservation of energy. I want a v, not a period. You still don't need to step on a scale before you get on the ride, if we ignore friction. And in real life, roller coasters are very well greased. They're not frictionless, but they're, you know, close enough that the mass doesn't play a big role. And I think we get this. V at the top is the square root of GR, of G times R. Yes? And I could crunch the numbers. I'm just going to leave that for a second because we're going to try and see if we can look for an algebraic pattern. If we need to plug in numbers later, we will. Now we're going to do conservation of energy. And I'm going to call this right here location big A, and I'm going to call this right here location big B. I could use final and initial. I'm worried if I use final, we're so used to final being on the ground that you might say final potential is 0. No, it's location A, location B. So my conservation of energy equation is going to look like this. Potential energy at A plus kinetic energy at A has to equal the potential energy at B plus the kinetic energy at B. Any of these, 0. Since I said minimum height, let's assume we're starting with no extra energy. All right. Are we cosmic here, or are we, so I don't need to use negative big G, big M, little m over, I can just use MGH? Oh, thank you. At location A equals MGH at location B plus a half MV at location B squared. Yay! Now, don't start filling stuff in. Just draw a great big fraction line, first of all. On the left, because I'm trying to get the height by itself, how would I get the height by itself? Wait a minute. Wait. Before I do that, get rid of that long fraction bar. Let's try going a little algebraic here first. I'm going to try rewriting this as GH at location A. That's a terrible A, Mr. Duke. G. The height at B, how could you describe that in terms of a radius? At location B, how high are we in terms of the radius? No. In terms of the radius. I don't want a numerical answer. Algebraically, in terms of the radius. Where did it come from? Okay, I'm going to write here a height of... Won't that be the case for any loop? If we're starting a loop out on the ground, its height is always going to be twice the radius at the top. Plus 0.5, there's my 1/2. And you know what? Instead of writing v squared, I have a lovely expression right here for v at the top. V at the top is the square root of GR. What would v squared be? Just plain old GR? And holy smokes, this hasn't happened in a long time. What cancels? Gravity? Are you serial? Really? What does that mean? It means, Shashan, if you designed this roller coaster here on the Earth, and it worked fine here on the Earth, and we had Star Trek technology and could beam it directly to Mars, it would work just fine with no adjustments in Mars' gravitational field. Or if you beamed it to the moon, it would work just fine, no adjustments in the moon's gravitational field, assuming you could do a workaround the whole vacuum, atmosphere, dying in space thing. But just as an intellectual experiment, this roller coaster would work just fine on the Sun, on Jupiter, on the Moon, on Neptune. Work just fine on any of those planets. Hasn't happened for a while that G canceled. Now, not only that, see, I think what we have then is H equals 2R plus 0.5R. Are those not like terms? What's 2 plus 0.5? 2.5. What's R plus R? Just, you know what? 2R plus 0.5R. I think our final answer, and this is about as clean an answer as you get. You know what the minimum height for a roller coaster with a circular loop is? Has to be 2.5 times the radius. I like that answer just because it's so clean. And I'm willing to bet anybody who engineers roller coaster rides, that's probably one of the things you have memorized. Now, again, Sebastian, for a clothoid loop, which is the kind of design now, it's not this. I'm sure it's more complicated, but you probably derive it from this. Do some calculus. Oh, in our particular answer then, I don't even need a calculator. It's 2.5 times 4. 2 times 4, 8. 0.5 times 4, 2. 8 and 2, Cole, in your head is? In our magic physics world with no friction and circular loops, if you're building a roller coaster and you want to start out from rest, the hill is always going to have to be 2.5 times whatever the radius of your loop is. As ugly as it could have been, that's about as clean an answer as you'll ever get here in Physics 12. Very nice. Part B says find the normal force at the bottom. We're going to skip that. So you can go back and you can go thunk. Example 2. Here's your toy car. Here's your Hot Wheels little loop-de-loop set. So at the top of a 12 centimeter, nice try, 0.12 meter radius loop, a 350 gram, nice try, 0.35 kilogram. Toy car experiences a force from the track of 2 newtons. Assume the cart is released from rest and that the track is frictionless. A, find its release height. B, find its speed at the top of the loop. What do they want us to find in A? Is there a change in height? Is there a change in speed? Is it a yucky, curvy track? This is a job for conservation of energy. But the 2 key spots are going to be location A and location B, top of the loop, because that's where they gave me the normal force at the track, top of the track. In fact, what are the forces acting here? Get the obvious one. I have mg, but there's also a small normal force pointing towards the center. Why pointing towards the center? Because the car is upside down, right? So, before I answer part A, I'm going to need to say gravity plus normal force equals mv squared over r. .35 times 9.8 plus 2 equals mv squared over r. I don't think I'm going to try and get the v by itself. I'm going to just crunch the whole left-hand side, get an answer, and then I'll times by r, divide by mass, and see what happens from there. 0.35 times 9.8 plus 2. I get 5.43 equals mv squared over r. So I guess v is going to end up being r 0.12 times 5.43 divided by a mass of 0.35, square root of that. Oh, I did times, Mr. Dewick. It's divided by. I get 1.3644. Carry a few extra digits here. 1.36445 if I round off properly, Cole. All right. That was preamble before we could even do A. A says find its release height. You know what? That means kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Are any of these 0? Oh, it says from rest. This is going to be mgh, and that's really at location A, equals a half mv at location B squared plus mgh at location B. Yay! Mass cancels. I don't think the G is going to cancel this time, though. In fact, the height, how would I get the height by itself? Here we can draw a big fraction line. We're going to divide by 9.8. It's going to be a 0.5 on the top. 1.36445 squared plus 9.8 times, oh, it's 2 radiuses. What was the radius? 12 centimeters for my height, 0.24, yeah? What do you get? I got this number stored still, so I'm going to go bracket 0.5 times this answer squared plus 9.8 times 0.24, close bracket, divided by 9.8. You get 33.5 centimeters, 0.335. Which, in terms of the dimensions of this particular track, Courtney, seem about right. The radius is 12 centimeters. If we wanted minimum, the answer would be 12 times 2.5 or 36. We don't want minimum. We're told there's some normal force, so sorry, 12 times 2.5 isn't 36. 12 times 2.5 is 30. For us to get a normal force, we need to start out a little bit higher than 30 centimeters, 33.5 centimeters. So that works if I do the rough calculations on the back of my head. What does B want us to find? We already did. That's really, yeah, 1.36445, 1.36. We had to do that to get A. Right? What would the speed be at the bottom? If they wanted that, I would ignore the loop and I would just go straight, put conservation of energy. Now that I know the height that I'm starting from, then I can now say still 0, mg times 33.5 equals a half mv final at the bottom squared, plus 0 if I'm at the bottom. I could solve for the speed at the bottom. I could also probably figure out the speed at the bottom by finding out how much kinetic energy and potential I had at the top, and I should get the same answer both ways. It'd be a way to check my answer. Turn the page. We're going to do a little thought experiment. Now, in this experiment, in this imaginary experiment, in real life, this would never happen, but humor me. Let's read. It says this: a satellite is in orbit around the Earth at radius big R and speed v, and it's a stable orbit. It's hit by a rock, and an amazing fluke, the rock pushes it away from the Earth into another stable orbit, or pushes it closer to the Earth into another stable orbit by slowing it down. So in an amazing fluke, this rock somehow moves it into another stable orbit. And all we know is it's at a lower speed. The question is this stable orbit A, the same as before in terms of radius? 2, bigger, further away from the Earth? Or 3, closer to the Earth? And I'm going to start out by saying, hey, it ain't that. In other words, here's what the question is really asking, Alejandro. If you're going slower in orbit, do you need to be further away from the Earth or closer to the Earth to stay in orbit? Let's find out. Did I say orbit? Then this is a job for right? And FG hasn't changed at all. That's still for this question, do I want to put the one that has the period in here, or do I want to put the one that has speed in here? Since we're talking about this satellite or it's slowing down, I want the v squared over r. Yay! A mass cancels. Yay! 1r cancels. But here, I don't want to get the v by itself. I want to get the r by itself, because I want to see how r is affected by the speed. How do I get the r by itself? I think the v squared and the r can just swap places, yes? So we get this. In fact, let's write that down here in our little space to right. R orb equals big G, big M, all over V orb squared. So here's the question. If that's how radius is related to orbital speed, if orbital speed gets smaller, if this term here gets smaller, what will happen to this overall answer? Show. Because you're dividing by a smaller number. In fact, you know what? Because there's a squared down there, if the orbital speed got twice as small, how much further from the Earth will we need to be? 4 times further. If the orbital speed is 3 times as small, we need to be 9 times further. In other words, the further from the Earth your orbit, the less kinetic energy you need. Oh, but it takes more potential to get it that far. So, you can't win no matter what, but it's still going to be expensive no matter what. The advantage with being further away from the Earth's orbit as well is, well, if you're further away and you're in a stable orbit, do you think the period would go up or go down? Because that, by the way, is really what we're interested in. When we put satellites up there, we're much less interested in how high they are. We're much more interested in how long they take to go around the Earth, because we want to know where they are at what time above what section of the Earth. I'll let you think about it. You can figure it out by going Fg equals m4 pi squared r over t squared and ask, how does radius change as a function of time? Period. You can figure it out yourself. Anyways, what did we say? The final orbital radius. Now, the odds of that happening, the odds that after a collision it would knock you further from the Earth into a stable orbit, really, really slim. The odds, really, what would probably happen is it would decrease your kinetic energy. And so now you don't quite have enough kinetic to stay in a stable orbit, and you would slowly start to spiral, 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 closer and closer and closer until you crash. However, if by a fluke you did end up in a stable orbit, I also have to point one more thing. My friend who typed this up said, technically, the final orbit actually is no longer circular after the collision. It's an ellipse which passes through the point where you collided with the asteroid and then moves closer to the Earth on the far side of the orbit. So what this does do, though, is it leads us to a little Star Trek physics. Back in the original series in the 60s, and in the first year of the Next Generation, they still had as their regular plot device, the Enterprise would be in standard orbit, there would be a warp engine problem, and they would be in danger of crashing into the planet. Why is that bad physics? If you're in standard orbit, are you running your engines at all? Do all our satellites up there have engines when they're in orbit? No. You can shut your engines off You can have a complete engine malfunction. You're in a stable orbit. They stopped writing, I think it was season 2, the physicists, when this next generation, the newer series came out, complained enough that they said, okay, we'll have, oh, the engine's fired in reverse. Yes, okay, now you've changed your kinetic energy. Now you're no longer in a stable orbit, or we'll hit something. Okay, now you're no longer in a stable orbit. We'll live with that. But the whole, especially in the 1960s, oh, our warp core is going to go. We're heading into the planet. You're fine. If you're in a stable orbit, you're fine. Doesn't matter if your warp core is going to go. You're fine. Oh, and the mass cancels. So even if you eject your warp core to now you have a lower mass, doesn't matter. We found little m canceled. You're fine. Example 3. Last one. A 965 kilogram satellite in orbit. You know what? That's important because that tells me that I can use Fg equals Fc and all sorts of stuff if I need to. Has a gravitational potential energy of that much? We need to make there's a couple of typos here. I finally fixed them and I keep forgetting to, but I did this morning. First of all, its potential energy would be negative because relative to 0 at infinity. Right? And where I wrote its orbital radius, okay, this is supposed to be times 10 to the 6th. I put the meters as an exponent instead of the 6. I was typing in a hurry, sorry. It happens. Now, I'm going to say I like this question, I like this question. And what I mean is, what I like about this question, which you will see on your test, here I'm giving you the potential energy or the orbital radius, and I'm saying, yeah, find the mass of the planet. I'm giving you part of the answer, go backwards and find the original information. Nice twist. And I think our starting point should be the fact that they gave us the gravitational potential energy. So when it says A, find the mass of the planet, I'm going to start out by going, well, right? And I'm going to get the big M by itself. I think mass of the planet. I think I'm going to times by R and divide by negative big G little m. Times by R, divide by negative big G little m. You know what? I'll just put the negative over there. I just know that. Oh, and this is one more reason why the gravitational potential energy had to be negative, because that will bring in a negative, and I already have a negative. I want two negatives because I want my mass to be positive because it's a scalar. Right? Okay, let's crunch the numbers. Mass of the planet is going to be negative, what's the orbital radius? 8.85 times 10 to the 6th. The potential energy is negative 6.55 times 10 to the 10th, divided by 6.67 times 10 to the negative 11, and little mass, I gave it to you, yes, 965 kilograms. How heavy is this? Oh, what kind of mass are we finding, by the way? A planet? Am I expecting a big answer or a small answer here? Yeah, if I'm like getting over 10 to the 10th, I'm probably a little nervous. I'm expecting something in the 10 to the 10th, 20th, 30th range even, right? So there's a, if you do wonky scientific notation, hopefully you'll catch it. Negative 8.856 times negative 6.55, yeah, negatives are going to cancel. 10 divided by bracket 6.67, negative 11 times 965. Oh! Almost 9 even. I'll carry a few extra sig figs and then go final answer. So I'm going to write 9.006 times 10 to the 24th, but that's going to be 9.0 times 10 to the 24th kilograms. just almost twice the size of the Earth. Right? The Earth is 6 times 10 to the 24th. 1.5 times the size of the Earth. Chase, what does B want me to find? Are we in orbit? Well, then good, find it. We're in orbit. That gives us our trigger, right? Find it on your own. See if you get the same thing as me. What was R? 8.85 times 10 to the 6. .8238 See if you get that. Sorry? What is, yes? We're good? What does C want us to find? Joe?
Kinetic energy is
Oh, that's a half mv squared. And that's, kinetic energy is not going to change all year. Now, it does change as you approach near light speeds, then relativity kicks in and you end up with an extra term starting to appear because your mass actually starts to increase and time dilate. Okay, fine. But this year, kinetic energy is going to be a half mv squared all year long. It's going to be a half, 0.5. Mass of the satellite was 965. Yes. V squared, I just figured it out, is going to be 8238.7 squared. It's going to be this number squared times 965 times 0.5 times 0.5. Oh! Works out fairly nice. 3.275 times 10 to, I guess I should go 3 sig figs. 3.28 times 10 to the 10th joules. Yeah? Vlad, what's D want me to find, kiddo? Total energy. Total energy is going to be potential plus kinetic. And they gave me potential in the question, did they not? It was negative. We added the negative. It was negative 6.55 times 10 to the 10th. And the kinetic is 3.275 times 10 to the 10th, positive. Oh! I guess I could have anticipated that, because we said, as our shortcut, which you may or may not want to use, it's up to you. If I take the potential energy in orbit, the kinetic energy is that number divided by 2 but positive, and the total energy is your potential divided by 2 but negative. Oops, I left off the negative in my final answer, Mr. Duick. Ha, there was my built-in error check too, catching myself for making a sloppy mistake. So I'm pretty sure I'm right. In fact, if you were, Seb, if I'd said 5 minutes left and you were doing this question, you might have just taken the number that they gave, the number that they gave you, that 6.55. You might have just taken this number here, quickly divided it by 2. There's your kinetic, flip a negative in front, there's your total. Yeah. What's your homework? 4, 5, 6, 7, 8. Nine B. So 4, 5, 6, 7, 8, 9B. Number 9, I like number 9. You're going to see number 9 on your test. I'm going to ask you how much work to end up in some kind of an orbit. Oh, and the work was done by the rocket engines. So when B says find the work done by the engines, it's really saying how much work? And you know what? I think I'll pause there. I think that's good. You got 15 minutes. You can work on the take-home quiz, and you can work on the homework, guys.